Water, the one substance every living creature on this planet cannot survive without. You drink it every single day, you bathe in it, you cook with it, you assume it is safe, clean, and simple. But what if everything you thought you knew about drinking water was only scratching the surface? What if the liquid sitting in your glass right now holds secrets so profound, so unexpected, that it could change the way you live your life forever? This is a journey into the surprising, the strange, and the absolutely mind-blowing world of drinking water, and once you start, you will never look at a glass of water the same way again. Please let us know in the comments where you are watching this video and what time you are watching it, and be sure to subscribe to the channel for future videos. Let us begin with something so fundamental, so breathtakingly enormous, that most people never stop to consider it. The water you drank this morning, that very sip of water that touched your lips today, is ancient. Not old, not aged, ancient beyond comprehension. The water molecules flowing through your body right now are roughly 4.5 billion years old. That is not an exaggeration. That is not poetic language. That is established science. The water on Earth today is largely the same water that has been here since the planet formed. It has cycled endlessly through clouds, oceans, rivers, glaciers, underground aquifers, and the bodies of countless organisms over billions of years. When you take a drink, you are consuming something older than the dinosaurs, older than the first single-celled organisms, older than the continents themselves. The glass of water in your hand is, in a very literal sense, as old as the Earth, and here is what makes that even more astonishing. Because water is constantly recycled through the hydrological cycle, evaporating, condensing, precipitating, flowing, the water you drink today has almost certainly been drunk before, by someone, by something. Statistically, some of the water molecules in your glass have passed through the bodies of dinosaurs. Some of those molecules were once part of an ancient ocean where the first fish swam. Some of them fell as rain on civilizations that no longer exist. Every sip connects you to every living thing that has ever existed on this planet. That is not mysticism. That is the water cycle operating over 4.5 billion years. Now consider this. Despite living on a planet that appears to be covered in water, a planet so blue from space that astronauts have called it a blue marble, the amount of water that is actually available for human consumption is shockingly small. About 71% of the Earth's surface is covered in water. That sounds like an almost infinite supply, but 97% of all that water is salt water, locked in the oceans, far too saline for humans to drink without extensive desalination processing. Of the remaining 3% that is fresh water, roughly 2/3 of it is frozen in glaciers and polar ice caps, inaccessible for everyday use. That leaves less than 1% of all the water on Earth available as freshwater for drinking, agriculture, sanitation, and every other human need. Less than 1%. The next time you turn on a faucet and clean water flows out, understand that you are accessing something extraordinarily rare on a planetary scale. And yet even within that tiny fraction of available freshwater, the distribution is staggeringly unequal. Some regions of the world are blessed with abundant freshwater supplies, while others face chronic shortages that affect every aspect of daily life. Around the globe, approximately 2 billion people live in countries experiencing high water stress. Over 700 million people worldwide lack access to clean, safe drinking water. Every single day, thousands of children under the age of 5 die from diseases directly linked to contaminated water and poor sanitation. These are not statistics from centuries ago. These are happening right now today as you listen to these words. Clean drinking water, something many of us take completely for granted, remains one of the most precious and unevenly distributed resources on the planet. But let us shift from the global to the personal, because the story of water inside your own body is just as remarkable as the story of water on the planet. Your body is made up of roughly 60% water. That is the average for an adult human, but that number fluctuates depending on age, sex, and body composition. Newborn babies are approximately 75% water. As we age, our water content decreases. By the time a person reaches elderly age, their body may be only about 50% water. You are in a very real sense a walking, talking, thinking vessel of water. Your brain alone is about 75% water. Your lungs are approximately 83% water. Even your bones, which feel so solid and rigid, are about 31% water. You are not a solid being. You are a water-based organism walking on a water-covered rock hurtling through space. Now here is something that will make you reach for a glass immediately. By the time you actually feel thirsty, your body is already dehydrated. That sensation of thirst is not an early warning system. It is a late alarm. Your body has already lost between 1 and 2% of its total water content before the thirst mechanism kicks in. And that seemingly small 1 to 2% loss is enough to impair your cognitive function, reduce your physical performance, and alter your mood. Studies have consistently shown that even mild dehydration, levels so slight that you would not feel particularly parched, can reduce concentration, increase feelings of anxiety, and cause headaches. Your brain is extraordinarily sensitive to changes in hydration. When researchers have tested subjects who were only mildly dehydrated, they found measurable declines in working memory, alertness, and the ability to perform mental arithmetic. Simply not drinking enough water can make you worse at your job, worse at studying, and worse at making decisions. The fix is as simple as drinking more water throughout the day, yet millions of people walk around in a state of chronic mild dehydration without ever realizing it. Speaking of how much water you should drink, let us address one of the most enduring myths in health and wellness. You have almost certainly heard the advice that you should drink 8 glasses of water a day. 8 glasses, 64 ounces. It is repeated everywhere by health magazines, wellness websites, well-meaning friends and family members. But here is the surprising truth. There is no solid scientific evidence behind the 8 glasses a day rule. No one is entirely sure where this recommendation originated, but researchers have traced it back to a 1945 report by the Food and Nutrition Board, which suggested that a suitable allowance of water for adults was approximately 2.5 liters per day. However, and this is the part everyone forgot, the very next sentence in that report stated that most of this quantity is contained in prepared foods. In other words, the recommendation included the water you get from eating fruits, vegetables, soups, and other foods. It was never meant to suggest that you needed to drink 8 separate glasses of pure water on top of everything else. Your actual water needs depend on your body's size, activity level, climate, diet, and overall health. Some people need more, some people need less. The best guide is not a rigid number, but rather your own body, the color of your urine, your level of thirst, and how you feel throughout the day. But while we are on the subject of how much water to drink, here is a fact that very few people know. You can actually die from drinking too much water. It is called water intoxication, or hyponatremia, and it occurs when you consume so much water in a short period of time that your kidneys cannot excrete it fast enough. The excess water dilutes the sodium levels in your blood to dangerously low concentrations. Sodium is an electrolyte that helps regulate the amount of water in and around your cells. When sodium levels drop too low, water moves into cells through osmosis, causing them to swell. Most cells can handle some swelling, but brain cells cannot because the skull leaves no room for expansion. The result can be seizures, coma, and death. There have been documented cases of athletes, particularly marathon runners, dying from hyponatremia because they drank excessive amounts of water during or after an event. A healthy adult's kidneys can process about 1 liter of water per hour. Drink significantly more than that consistently, and you enter dangerous territory. Water, the very substance of life, can kill you if consumed in excess. It is a powerful reminder that even the healthiest things can become harmful when taken to extremes. Now let us talk about something that happens to every human body every single day, but that most people never think about: the journey water takes through your system after you drink it. When you take a sip of water, it first enters your mouth and travels down your esophagus into your stomach. From there, the majority of water absorption happens in the small intestine. Water molecules pass through the walls of the intestine into the bloodstream remarkably quickly. Within about 5 minutes of drinking water on an empty stomach, your body begins absorbing it. Within 15 to 20 minutes, a significant portion has entered your bloodstream. Your blood then carries this water to every organ, every tissue, every cell in your body. It delivers nutrients, carries away waste products, regulates your body temperature, lubricates your joints, cushions your brain and spinal cord, and participates in countless chemical reactions. Eventually, the water is filtered by your kidneys, which process an astonishing 120 to 150 quarts of blood every single day. From that enormous volume, the kidneys produce about 1 to 2 quarts of urine, which carries waste products out of the body. The rest of the water is recirculated. Your body is an incredibly efficient water recycling system, and it is working every second of every day without you ever having to think about it. And here's a related fact that most people find genuinely surprising. Your kidneys are not the only way your body loses water. In fact, you lose water constantly through several pathways, and some of them are completely invisible to you. You lose water through your skin, even when you're not sweating, through a process called insensible perspiration. You lose water every time you exhale. That visible cloud of moisture you can see in cold weather is water vapor leaving your lungs. You lose water through your digestive system. An average person loses approximately 2 to 3 liters of water per day through all these combined routes, and during hot weather or intense physical activity, that number can increase dramatically. Soldiers operating in desert conditions can lose over a liter of sweat per hour. Professional athletes can lose 2 to 3 liters per hour during intense exercise. The body's need for water is relentless, and failure to replace what is lost leads to a cascade of problems that begin with fatigue and end, if unchecked, with organ failure and death. Let us stay with the human body for a moment, because there is an astonishing fact about how long a person can survive without water. The human body can survive for weeks without food, depending on body fat reserves and conditions. Some people have survived more than 2 months without eating. But without water, most people would die within 3 to 5 days. In extreme heat, death from dehydration can occur in as little as 24 hours. The human body simply cannot function without water. It is needed for every biochemical process, every cellular function, every organ system. A person who is deprived of water will first experience intense thirst, then dry mouth, then decreased urine output, then dizziness, confusion, rapid heartbeat, and eventually delirium, organ failure, and death. The progression is swift and merciless. No other substance is so immediately essential to human survival. You can live without shelter for days. You can live without food for weeks. But water, you have at most a handful of days. Here is something that connects the water inside your body to the water you drink from your tap or bottle, and it is one of the most important developments in human history. The practice of treating and purifying drinking water is actually relatively recent. For most of human history, people drank water directly from rivers, lakes, streams, and wells with no treatment whatsoever. They often got sick. They often died. Waterborne diseases like cholera, typhoid fever, and dysentery killed millions of people throughout history and continue to kill people in parts of the world today. It was not until the late 1800s and early 1900s that cities began implementing water treatment processes like filtration and chlorination. The introduction of chlorine to public water supplies in the early 20th century is considered one of the greatest public health achievements in human history. It has been estimated that water chlorination and filtration have been responsible for a significant portion of the increase in life expectancy in developed nations over the past century. Before these treatment methods were adopted, it was not unusual for large portions of urban populations to be sickened or killed by contaminated water. Clean drinking water is not a natural state of affairs. It is an engineered triumph, one that required decades of scientific discovery, infrastructure development, and public investment. And speaking of chlorine in your water, here is something most people do not realize. The chlorine that is added to public water supplies to kill harmful bacteria and pathogens does not fully dissipate before the water reaches your glass. You are drinking trace amounts of chlorine every day. In most developed nations, the levels are carefully controlled and are considered safe for human consumption, but the chlorine is there and you can sometimes taste it. that faintly chemical taste or smell that tap water sometimes has. That is chlorine. And chlorine does not just kill harmful microorganisms. It can react with naturally occurring organic matter in the water to form byproducts called trihalomethanes and halocetic acids. Long-term exposure to high levels of these byproducts has been linked in some studies to an increased risk of certain cancers and reproductive problems. This is one reason that many people choose to filter their tap water before drinking it. A simple activated carbon filter, the type found in most consumer water pitchers, can remove much of the chlorine and its byproducts while leaving beneficial minerals intact. It is a small step that can make a meaningful difference in the quality of the water you consume, but chlorine is only one of the many things that might be in your drinking water. Modern water testing has revealed that tap water can contain a surprisingly wide array of substances. Depending on where you live and the source of your water, your tap water might contain trace amounts of lead, copper, arsenic, fluoride, nitrates, pesticide residues, pharmaceutical compounds, microplastics, and dozens of other substances. Lead contamination, in particular, remains a serious concern in many communities that have older infrastructure. Lead can leach into drinking water from old pipes, solder, and fixtures. Even at low levels, lead exposure is harmful, particularly to children, where it can cause developmental delays, learning difficulties, and behavioral problems. There is no safe level of lead exposure for children. None. The fact that lead pipes still deliver drinking water to homes in many places is one of the most urgent infrastructure challenges of our time. Now here is a fact about water that will fundamentally change how you think about your morning routine. Hot water from your tap is more likely to contain contaminants than cold water. This is because hot water dissolves metals and other substances from pipes more readily than cold water does. If your home has lead pipes, lead solder, or brass fixtures that contain lead, running hot water through them will leach significantly more lead into the water than running cold water. This is why health authorities recommend that you always use cold tap water for drinking, cooking, and especially for preparing baby formula. That hot water from the tap might feel convenient for making a quick cup of tea, but it may carry a higher load of dissolved metals and contaminants. Let the cold water run for a few seconds to flush out water that has been sitting in the pipes, and then use that cold water for consumption. It is a simple practice that many people are unaware of, and it can reduce your exposure to harmful substances. Let us pivot to something equally surprising but in a completely different direction. Bottled water. It is a massive global industry worth hundreds of billions of dollars. People buy bottled water because they believe it is cleaner, safer, or healthier than tap water. But studies have repeatedly shown that much of the bottled water sold worldwide is simply filtered tap water. That is right, many major bottled water brands source their water from municipal supplies, the same water that comes out of your faucet at home, run it through additional filtration processes, and sell it to you at a markup of several hundred to several thousand%. In many cases, the tap water in developed nations is subject to more rigorous and frequent testing than bottled water, which is regulated differently and often less strictly. You may be paying a premium for water that is no better and in some cases potentially worse than what flows freely from your kitchen sink. And here is the environmental cost of that bottled water habit. The production of plastic water bottles consumes enormous amounts of energy and resources. It takes approximately 3 liters of water to produce a single 1-liter bottle of water when you factor in the manufacturing process. The plastic itself is derived from petroleum. The bottles must be transported, often over long distances, burning fossil fuels every mile of the way. And after a single use, the vast majority of those plastic bottles are not recycled. Globally, roughly 1 million plastic bottles are purchased every single minute. Every minute, the majority of those bottles end up in landfills or, worse, in the ocean. Plastic pollution is now found in the deepest ocean trenches, on the most remote islands, and inside the bodies of marine animals worldwide. Single-use plastic water bottles are one of the largest contributors to this crisis. The irony is staggering. In the pursuit of clean water, we are polluting the planet's water systems with plastic. And now, speaking of plastic, here is a fact that has only recently come to light and is deeply concerning. Microplastics, tiny fragments of plastic less than 5 millimeters in size, have been found in drinking water around the world. Both tap water and bottled water contain them. A study by the World Health Organization found microplastics in 90% of bottled water samples tested from major brands. Tap water samples from cities around the world also showed microplastic contamination, though generally at lower levels than bottled water. These tiny plastic particles come from the breakdown of larger plastic items, from synthetic clothing fibers released during washing, from vehicle tire wear, and from many other sources. They are now so pervasive in the environment that they have been found in rain, in snow, in remote mountain lakes, and in the air we breathe. The health effects of consuming microplastics are still being studied, but early research suggests they could carry harmful chemicals into the body and potentially cause inflammation at the cellular level. You are almost certainly drinking microplastics right now, and science is only beginning to understand what that means for human health. Let us now turn to one of the most debated topics in the world of drinking water: fluoride. Many public water systems add fluoride to drinking water as a public health measure to reduce tooth decay. This practice, known as water fluoridation, began in the 1940s and has been credited with significantly reducing rates of cavities and dental disease, particularly among children and low-income populations who might not have regular access to dental care. Major health organizations around the world have endorsed water fluoridation as safe and effective. However, fluoride in drinking water has also been the subject of intense controversy. Critics argue that adding a chemical to public water supplies amounts to mass medication without individual consent. Some studies have raised concerns about potential health effects of long-term fluoride exposure at higher levels, including possible links to thyroid problems and, in some research, effects on neurodevelopment in children. The debate continues, and it highlights a fundamental tension in public health: the balance between collective benefit and individual choice. Whether you support fluoridation or oppose it, the fact that this single element in drinking water has generated decades of passionate debate reveals just how personal and political the subject of water can become. Now let us take a step back from the chemistry and politics of water and look at something purely physical, because water itself is one of the strangest substances in the known universe. Most liquids contract as they cool. Water does too, but only up to a point. When water cools below 4 degrees Celsius, about 39 degrees Fahrenheit, it begins to expand instead of continuing to contract. And when it freezes into ice, it expands even further, becoming about 9% less dense than liquid water. This is why ice floats, and if you think about it, this is one of the most consequential quirks of physics in the history of life. If ice were denser than water, as the solid form of almost every other substance is denser than its liquid form, ice would sink. Lakes and oceans would freeze from the bottom up instead of from the top down. The ice at the bottom would be insulated from the sun and might never melt. Over time, entire bodies of water could freeze solid, making aquatic life impossible. The fact that ice floats creates an insulating layer on the surface of frozen bodies of water, keeping the water beneath liquid and allowing fish and other organisms to survive winter. This single unusual property of water may be one of the reasons life exists on Earth at all. Water has other extraordinary physical properties as well. It has an unusually high specific heat capacity, meaning it can absorb a great deal of heat energy before its temperature rises significantly. This is why large bodies of water moderate the climate of nearby land areas. Coastal cities experience milder temperatures than inland cities because the ocean absorbs and releases heat slowly. It is also why water is used as a coolant in engines, power plants, and industrial processes. Your body exploits this same property. The water in your bloodstream absorbs excess heat from your muscles and organs and distributes it throughout your body, helping maintain a stable internal temperature. When you overheat, your body releases water through sweat, and the evaporation of that sweat from your skin's surface carries heat away from your body, a remarkably efficient cooling mechanism. Water also has exceptionally high surface tension compared to most other liquids. This is because water molecules are strongly attracted to each other through hydrogen bonding. This high surface tension is what allows small insects to walk on water. It is what causes water to form droplets rather than spreading out into a thin film. And it is a key factor in capillary action, the ability of water to move upward against gravity through narrow spaces. Capillary action is how water travels from the roots of a tree all the way up to its highest leaves, sometimes over 100 meters in the tallest trees. Without the surface tension and cohesive properties of water, plants as we know them could not exist. And without plants, neither could the ecosystems that depend on them, including human civilization. Here is another fascinating physical property of water that you encounter every day without thinking about it. Water is sometimes called the universal solvent because it dissolves more substances than any other common liquid. This is because of its polar molecular structure. The oxygen atom in a water molecule carries a slight negative charge, while the hydrogen atoms carry slight positive charges. This polarity allows water to interact with and dissolve a wide variety of substances, from salts and sugars to gases and many organic compounds. This property is what makes water so essential for biological processes. It dissolves nutrients so they can be transported through organisms. It dissolves waste products so they can be eliminated, and it provides the medium in which the vast majority of biochemical reactions take place. But this same property also means that water is incredibly effective at picking up contaminants. As water flows through the environment, over rocks, through soil, past agricultural fields, through industrial areas, it dissolves and carries along whatever it encounters. This is why water purification is so important and so challenging. Water's greatest strength as a biological medium is also its greatest vulnerability as a potential carrier of pollutants. Now let us talk about something that many people experience but few understand: why water from different sources tastes different. You have ever traveled to a different city and noticed that the tap water tastes different from what you are used to at home? You are not imagining it. The taste of water is determined by its mineral content and the dissolved substances it contains. Water that flows through limestone formations picks up calcium and magnesium, which give it a slightly sweet mineral taste and also make it what is known as hard water. Water from granite regions tends to be softer and may taste smoother or more neutral. Water that has been heavily chlorinated will have a noticeable chemical taste. Water with higher iron content might taste slightly metallic. The pH of water also affects its taste. Slightly alkaline water tends to taste smoother, while slightly acidic water may taste sharper or more crisp. There is no single correct taste for water, and people's preferences are largely shaped by what they grew up drinking. What tastes normal and refreshing to you might taste strange or off-putting to someone from a different region, simply because you are each accustomed to a different mineral profile. Speaking of minerals in water, here is something that surprises many people. Drinking water can be a significant source of essential minerals. Depending on its source, water can contain meaningful amounts of calcium, magnesium, potassium, sodium, and other minerals that your body needs. Some mineral-rich spring waters contain enough calcium that drinking a liter or two per day contributes measurably to your daily calcium intake. Magnesium in water has been studied for its potential cardiovascular benefits. Some research has found correlations between higher magnesium levels in drinking water and lower rates of heart disease. This is one reason why some health professionals express concern about the growing trend toward drinking highly purified or distilled water. While these purification methods remove contaminants, they also strip out beneficial minerals. Drinking only distilled or reverse osmosis purified water without other dietary sources of minerals could, over time, contribute to mineral deficiencies. Water is not just hydration, it can be nutrition. Let us now explore the temperature of the water you drink, because there are some fascinating and often misunderstood aspects to this. In many East Asian cultures, there is a strong tradition of drinking warm or hot water rather than cold water. The belief is that cold water can shock the system, slow digestion, and harm the body's internal balance. In Western cultures, ice-cold water is the norm, and many people find it more refreshing and palatable. So who is right? The science suggests that both have some validity, depending on the context. Cold water is absorbed slightly more quickly by the body and can help cool you down more effectively during exercise or in hot conditions. During physical activity, cold water has been shown to help regulate body temperature and improve performance. However, warm water may have benefits for digestion. Some studies have found that warm water can help relax the smooth muscles of the digestive tract and improve the movement of food through the intestines. Warm water can also help dissolve and break down food more effectively than cold water. For everyday hydration, the temperature matters less than the fact that you are drinking enough in the first place. The best temperature for your water is whatever temperature makes you most likely to drink an adequate amount. Here is a fact about water that connects to human history in a profoundly important way. The location of water sources has shaped the development of human civilization more than almost any other single factor. Every major ancient civilization, the Egyptians along the Nile, the Mesopotamians between the Tigris and Euphrates, the Indus Valley Civilization, the ancient Chinese along the Yellow River, arose along the banks of major rivers. Water was needed for drinking, of course, but also for irrigation, transportation, sanitation, and defense. Cities grew where water was abundant. Trade routes followed rivers and coastlines. Wars were fought over access to water sources. The Roman Empire built some of the most impressive water infrastructure in ancient history. Their aqueduct system stretched over 250 miles and delivered over 200 million gallons of water per day to the city of Rome. Some of those aqueducts are still standing 2,000 years later, a testament to both the engineering skill of the Romans and the absolute centrality of water to urban life. The history of human civilization is in many ways the history of how humans have managed to secure reliable supplies of drinking water, and that history includes some dark chapters. Throughout the ages, water has been used as a weapon. Armies have poisoned wells to deny water to their enemies. Besieging forces have cut off water supplies to force cities into submission. In more recent history, industrial pollution has contaminated water sources on which entire communities depend, sometimes deliberately, sometimes through negligent disregard for public health. The poisoning of water is one of the oldest and most devastating acts of warfare and exploitation, and it continues in various forms today. Access to clean water is not just a matter of geography or infrastructure. It is a matter of power, politics, and human rights. Let us shift to something more immediate and practical. The water you drink interacts with your body in ways that go far beyond simple hydration. Water plays a critical role in your body's ability to flush out toxins and waste products. Your kidneys, as we discussed, filter your blood continuously, removing waste and excess substances and excreting them in urine. But your kidneys can only function properly when they have enough water to work with. When you are dehydrated, your kidneys conserve water by producing more concentrated urine. Over time, chronic dehydration forces the kidneys to work harder and can contribute to the formation of kidney stones, hard deposits of minerals and salts that form inside the kidneys and can be extraordinarily painful to pass. Studies have consistently shown that people who drink more water have a significantly lower risk of developing kidney stones. In fact, increasing water intake is one of the most commonly recommended preventive measures for people who are prone to kidney stones. Something as simple as drinking an extra glass or two of water each day can spare you from one of the most painful medical conditions known. And while we are talking about the kidneys, here is something remarkable. Your kidneys filter approximately 50 gallons of blood every single day. 50 gallons. From that enormous volume, they produce only about 1 to 2 quarts of urine. That means your kidneys are reabsorbing the vast majority of the water and useful substances from your blood and only excreting what the body does not need. The precision of this process is extraordinary. Your kidneys can adjust the concentration of your urine over a wide range, from very dilute when you have been drinking a lot of water to very concentrated when you are dehydrated. They can selectively retain or excrete sodium, potassium, calcium, and dozens of other substances based on what your body needs at any given moment. Your kidneys are, in effect, the most sophisticated water treatment plant on the planet, operating 24 hours a day, 7 days a week, with an efficiency that no human-engineered system can match. Now let us discuss something that affects every person differently but that very few people talk about: the connection between water and your skin. Your skin is the largest organ in your body, and it is approximately 64% water. When you are well hydrated, your skin is more elastic, more resilient, and better able to perform its function as a barrier against the outside world. Dehydration shows up in your skin as dryness, tightness, and reduced elasticity. Severely dehydrated skin can crack and become vulnerable to infection. While drinking water alone will not cure all skin problems or reverse aging, despite what some beauty marketing might claim, maintaining proper hydration is genuinely important for skin health. Your skin loses water constantly through evaporation, and if that water is not replaced from within, your skin's condition will deteriorate. It is one of the most visible indicators of hydration status. Well-hydrated people tend to have skin that looks healthier and more vibrant, while chronically dehydrated people often have skin that appears dull and dry. Here is another connection between water and your body that you might not have considered: water and your joints. The cartilage in your joints, the smooth, rubbery tissue that cushions the ends of your bones and allows them to glide smoothly against each other, is approximately 80% water. When you are well hydrated, your cartilage remains supple and effective at absorbing shock. When you are chronically dehydrated, your cartilage can become less effective, leading to increased friction between bones, greater wear and tear, and potentially more joint pain. Synovial fluid, the lubricating fluid inside your joints, is also primarily water. Adequate hydration helps maintain the volume and viscosity of this fluid, keeping your joints moving smoothly. If you experience joint stiffness or pain, particularly in the morning or after periods of inactivity, inadequate hydration could be a contributing factor that is easily addressed. Let us now venture into territory that is genuinely mind-bending. The water molecule itself, H2O, is one of the simplest chemical compounds in existence. Just 2 hydrogen atoms bonded to 1 oxygen atom. Yet from this simplicity arises one of the most complex and unusual substances in the known universe. Water exists naturally in all 3 states of matter on Earth's surface: as a solid in ice, as a liquid in water, and as a gas in water vapor. No other common substance does this within the range of temperatures normally found on our planet's surface. This triple existence is what drives the water cycle, the continuous movement of water between the atmosphere, the land, and the oceans, which in turn drives weather patterns, shapes landscapes, supports ecosystems, and makes life possible. Water also has what scientists call anomalous properties, behaviors that are unusual or unexpected compared to similar substances. We already discussed the fact that ice is less dense than liquid water, which is highly unusual. But water is also anomalous in its boiling point. Based on its molecular weight and the properties of similar compounds like hydrogen sulfide and hydrogen selenide, water should be a gas at room temperature. If it followed the trends set by these related compounds, water would boil at around -70 degrees Celsius, meaning it would exist only as a gas under normal conditions on Earth. The reason water is a liquid at room temperature is because of hydrogen bonding, the unusually strong attraction between the slightly positive hydrogen atoms of one water molecule and the slightly negative oxygen atom of neighboring molecules. These hydrogen bonds give water a much higher boiling point than it would otherwise have, which is the only reason liquid water, and therefore life as we know it, exists on this planet. The very existence of liquid water, and therefore the very existence of you, depends on the peculiar strength of hydrogen bonds. Let us move from the molecular scale to something you can see with your own eyes. Have you ever noticed that a glass of water left sitting on a counter overnight tastes different in the morning? That flat, slightly stale taste is not your imagination. When water sits exposed to air, it absorbs small amounts of carbon dioxide from the atmosphere. The carbon dioxide dissolves in the water and forms a weak carbonic acid, slightly lowering the pH of the water and giving it a subtly different taste. Additionally, when chlorinated tap water sits out, some of the chlorine can dissipate, further changing the taste profile. The temperature change from cold to room temperature also affects how you perceive the taste. None of these changes make the water unsafe to drink, but they do alter its flavor enough that most people can notice the difference. It is a small but tangible example of water's remarkable ability to interact with and absorb substances from its environment. Here is a fact about water that touches on something deeply personal: water and mental health. Research has increasingly shown that hydration status has a significant effect on mood and emotional well-being. Studies have found that even mild dehydration can increase feelings of anxiety, tension, and fatigue. In one study, researchers found that women who were only about 1% dehydrated experienced degraded mood, increased perception of task difficulty, lower concentration, and more headaches. A similar study in men found that mild dehydration produced adverse changes in vigilance and working memory, along with increased tension and anxiety. Depression and water intake have also been studied. Some research has found correlations between low water intake and higher rates of depression, though the relationship is complex and influenced by many other factors. The takeaway is clear, though: if you're feeling mentally foggy, anxious, or fatigued, one of the simplest things you can do before reaching for caffeine or medication is drink a glass of water. It will not solve every problem, but it might solve more problems than you expect. Now let us explore a truly stunning fact about water and agriculture. It takes an enormous amount of water to produce the food you eat, far more than most people realize. This is known as virtual water or embedded water, and the numbers are staggering. To produce a single pound of beef requires approximately 1,800 gallons of water. That includes the water the animal drinks, the water used to grow the feed crops, and the water used in processing. A single pound of chicken requires about 500 gallons. A pound of rice takes about 450 gallons. Even seemingly simple foods require significant water. A single apple requires about 18 gallons, a single egg about 50 gallons, and a single slice of bread about 10 gallons. When you sit down to dinner, you are consuming not just the food on your plate, but the hundreds or thousands of gallons of water that were needed to produce it. Global food production accounts for approximately 70% of all freshwater withdrawals worldwide. When people talk about water scarcity, they are often really talking about food scarcity, because the two are inextricably linked. And here's something that connects water and energy in a way most people never think about. Producing energy requires enormous amounts of water, and producing clean water requires enormous amounts of energy. This is called the water-energy nexus, and it is one of the most important challenges facing the modern world. Thermoelectric power plants, including coal, natural gas, and nuclear plants, use water for cooling, and they are among the largest consumers of freshwater in many countries. Hydroelectric power, of course, depends entirely on water. Even renewable energy sources like solar panels and wind turbines require water in their manufacturing processes. On the flip side, treating, pumping, and distributing clean water to homes and businesses requires significant energy. Wastewater treatment also requires energy. The two resources are deeply intertwined, and stresses on one inevitably create stresses on the other. As populations grow and climate patterns shift, managing this nexus is becoming increasingly critical. Let us talk about something that sounds like science fiction but is absolutely real. Water has memory. Well, sort of. Not in the mystical sense that some alternative health practitioners have claimed. The idea that water can remember substances it once contained, even after being diluted beyond the point where a single molecule of that substance remains, has been thoroughly debunked by rigorous scientific investigation. However, water does have remarkable structural properties that are still being studied. When water interacts with different surfaces and substances, its hydrogen bond network can adopt different configurations. The structure of water near a hydrophobic surface is different from the structure of water near a hydrophilic surface. Water near protein surfaces in your body adopts specific structural configurations that are important for biological function. So while water does not have memory in any meaningful sense, it is structurally far more complex and responsive to its environment than most people realize. Here is a fact that will make you think twice about what you are drinking. Pharmaceutical compounds have been detected in drinking water supplies around the world. When people take medications, their bodies do not absorb 100% of the active ingredients. The remainder passes through in urine and feces and enters the wastewater system. Many pharmaceutical compounds are not fully removed by conventional wastewater treatment processes, so they end up in rivers, lakes, and groundwater, the same sources from which drinking water is drawn. Studies have detected trace amounts of antibiotics, hormones, antidepressants, painkillers, and many other pharmaceuticals in tap water supplies in cities across the globe. The concentrations are extremely low, typically measured in parts per trillion, and most health authorities say the levels are too low to pose an immediate health risk. But the long-term effects of chronic low-level exposure to a cocktail of pharmaceutical compounds through drinking water are not well understood. It is an emerging area of research that many scientists consider one of the most important water quality challenges of the coming decades. Now here is a fact that connects water to the very air you breathe. The water cycle is responsible for distributing fresh water around the planet, and it operates on an almost incomprehensible scale. Every day, the sun evaporates approximately 1 trillion tons of water from the Earth's surface, from oceans, lakes, rivers, soil, and plants. That water vapor rises into the atmosphere, is carried by wind currents, condenses into clouds, and eventually falls back to Earth as precipitation, rain, snow, sleet, or hail. The total amount of water vapor in the atmosphere at any given moment is approximately 12,900 cubic kilometers. If all of that atmospheric water were to fall as rain at once, it would cover the entire Earth's surface to a depth of about 1 inch. The water cycle moves such vast quantities of water that it plays a dominant role in shaping weather patterns and climate. Every rainstorm, every snowfall, every drought is a manifestation of the water cycle in action. Something most people never consider is that the water coming from their tap has been through an extraordinarily long and complex journey before it reaches them. Depending on the source, your drinking water might have started as snow falling on a mountain range hundreds of miles away, melted into a stream, flowed into a river, been diverted into a reservoir, sat in that reservoir for months or even years, been drawn into a treatment plant, passed through coagulation, sedimentation, filtration, and disinfection processes, been pumped through miles of underground pipes, and finally arrived at your faucet. The infrastructure required to accomplish this, the dams, reservoirs, treatment plants, pumping stations, and distribution networks, represents one of the most massive and expensive engineered systems in human history. Most of it is underground, invisible, and taken entirely for granted. The next time you turn on your faucet and clean water appears, take a moment to appreciate the extraordinary chain of events, engineering, and investment that made it possible. Let us discuss a topic that is becoming increasingly urgent around the world: groundwater depletion. Much of the world's freshwater supply comes not from surface sources like rivers and lakes, but from underground aquifers, vast subterranean reservoirs of water stored in porous rock and sediment. These aquifers accumulated their water over thousands or even millions of years, slowly filled by rainfall that percolated down through the soil. In many parts of the world, humans are now pumping water out of these aquifers far faster than nature can replenish them. The Ogallala Aquifer, one of the world's largest underground freshwater reserves, stretches beneath the Great Plains and provides water for agriculture and communities across a vast area. But decades of heavy pumping have significantly drawn down its water levels, and in some areas, it could be substantially depleted within a few decades if current trends continue. Around the world, satellite data from space has revealed that many of the planet's major aquifers are being depleted at alarming rates. This is groundwater that took thousands of years to accumulate, being consumed in a few generations. When an aquifer is depleted, there is no quick fix. The water is simply gone for practical purposes, and communities that depend on it face a crisis. Here is something both remarkable and underappreciated: the role of water in your digestive system. You need water to digest food properly. Saliva, which is the first step in digestion, is 99% water. Saliva contains enzymes that begin breaking down food in your mouth, and without adequate water, saliva production decreases, making it harder to chew, swallow, and begin the digestive process. In the stomach, water helps dissolve nutrients and aids in the chemical breakdown of food by gastric acids. In the intestines, water is essential for the absorption of nutrients into the bloodstream and for the smooth passage of food through the digestive tract. Insufficient water intake is one of the most common causes of constipation. Without enough water, the colon absorbs more water from the stool, making it hard, dry, and difficult to pass. Simply drinking more water can resolve many cases of chronic constipation without any need for medication. Your digestive system is, at every stage, dependent on water. Let us talk about something that many people find hard to believe when they first hear it. You can survive on seawater, but not by drinking it directly. The salt concentration in seawater is approximately 3.5%, which is far higher than what your kidneys can efficiently process. If you drink seawater, your body actually has to use more water to flush out the excess salt than it gains from the seawater itself. The result is net water loss. You become more dehydrated, not less. This is why shipwreck survivors who drink seawater actually die faster than those who drink nothing at all. However, seawater can be made drinkable through desalination, a process that removes the salt and other dissolved minerals. Desalination technology has improved dramatically in recent decades, and there are now large-scale desalination plants operating in water-scarce regions around the world, producing millions of gallons of drinking water per day from seawater. The process remains energy-intensive and expensive compared to treating freshwater, but as freshwater sources come under increasing pressure, desalination is likely to play an increasingly important role in global water supply. Here is a fact about water that reveals something profound about the human body's intelligence. Your body has an incredibly sophisticated system for maintaining its water balance. Receptors in your brain, specifically in the hypothalamus, constantly monitor the concentration of your blood. When the concentration rises, indicating that you are becoming dehydrated, the hypothalamus triggers the sensation of thirst and also signals the pituitary gland to release antidiuretic hormone, which tells your kidneys to reabsorb more water and produce more concentrated urine. When the concentration drops, indicating excess water, the hypothalamus reduces the thirst sensation and decreases the release of antidiuretic hormone, allowing the kidneys to excrete more dilute urine. This feedback loop operates continuously, adjusting your body's water balance with remarkable precision. It is one of the most elegant regulatory systems in human physiology, and it works so seamlessly that most people are completely unaware of its existence. Let us explore a fascinating area where water science meets everyday life: the hardness of water and its effects. Water hardness refers to the concentration of dissolved minerals, primarily calcium and magnesium, in the water. Hard water has high mineral content, soft water has low mineral content. The hardness of your water depends on the geology of the region where your water originates. Water that has flowed through limestone, chalk, or dolomite formations tends to be hard. Water from granite or volcanic regions tends to be soft. Hard water is not harmful to drink. In fact, as we discussed, the minerals it contains can be beneficial to your health. However, hard water causes problems in many household applications. It leaves mineral deposits called limescale on fixtures, inside pipes, and in appliances like water heaters, kettles, and dishwashers. It makes soap less effective, requiring more soap for cleaning and often leaving a residue on skin, hair, and clothing. It can affect the taste and appearance of coffee and tea. Many households install water softeners to address these problems, but it is worth noting that the softening process typically replaces calcium and magnesium with sodium, which has its own health implications for people on sodium-restricted diets. And now, here is something that crosses into the realm of the truly extraordinary: water and sound. Water responds to sound vibrations in ways that can be visually observed. The field of cymatics, the study of visible sound vibration patterns, has demonstrated that when water is placed on a vibrating surface, it forms geometric patterns that change with the frequency of the sound. At different frequencies, water creates different shapes: concentric rings, star patterns, hexagonal grids, and increasingly complex geometric configurations at higher frequencies. While some people have extrapolated from these observations to make unsubstantiated claims about water being influenced by human emotions or intentions, the underlying physical phenomenon is real and well documented. Water is an excellent medium for transmitting sound waves. Sound travels approximately 4 times faster through water than through air, at about 1,500 meters per second compared to about 340 meters per second in air. This is why whales can communicate over distances of hundreds of miles through the ocean. Here is a fact that connects water to the very question of life beyond Earth. When scientists search for signs of life on other planets and moons in our solar system, the first thing they look for is water. This is because, as far as we know, water is an absolute prerequisite for life. Every known form of life on Earth requires liquid water to survive. When NASA announced the discovery of evidence for liquid water flowing on the surface of Mars, it was headline news around the world, because where there is water, there might be life. Jupiter's moon Europa is believed to have a vast ocean of liquid water beneath its icy surface, making it one of the most promising places to search for extraterrestrial life in our solar system. Saturn's moon Enceladus has geysers that shoot water vapor into space, also suggesting a subsurface ocean. The search for water in the universe is fundamentally a search for life, because in every environment on Earth where scientists have found liquid water, no matter how extreme the conditions, they have found life. From boiling hot springs to freezing Antarctic lakes, from deep-sea hydrothermal vents to acidic mine drainage, wherever there is liquid water, life finds a way. Let us now talk about something that affects billions of people every day but rarely makes headlines: water and cooking. The quality of the water you use in cooking directly affects the quality of the food you prepare. Professional chefs know this well. The minerals and chemicals in water affect the flavor and texture of everything from bread to pasta to coffee. Hard water can make bread dough tougher because the minerals strengthen the gluten structure. Soft water can make bread dough stickier and weaker. The chlorine in tap water can inhibit the fermentation process in bread making by suppressing yeast activity. Coffee experts insist that the mineral content of water is one of the most important factors in brewing a great cup of coffee. Too few minerals and the coffee tastes flat, too many and it tastes bitter or harsh. The Specialty Coffee Association has even published guidelines for the ideal mineral content and pH of water for coffee brewing. When you cook pasta, the minerals in the water affect the texture and flavor of the noodles. When you make soup or stock, the water is a primary ingredient and its quality shines through. The next time you prepare food, remember that water is not just a passive medium. It is an active ingredient that shapes the final result. And here's something that might change your morning routine forever. The first glass of water you drink in the morning, right after waking up, may be one of the most important glasses of water you drink all day. During sleep, your body continues to lose water through breathing, perspiration, and other processes. By the time you wake up, you have gone 6 to 8 hours without any water intake, and you are mildly dehydrated. Drinking a glass of water first thing in the morning helps rehydrate your body, kickstarts your metabolism, helps flush out toxins, fuels your brain with the hydration it needs to function optimally, and can help stimulate bowel movements. In many cultures around the world, drinking water upon waking is a traditional health practice that has been followed for centuries. Modern science is beginning to confirm what these traditions have long suggested. Starting your day with water is one of the simplest and most effective health habits you can adopt. Let us discuss a topic that sounds futuristic but is already here: water recycling, or more specifically, the concept of drinking recycled wastewater. This idea provokes a visceral reaction in many people. The idea of drinking water that was once sewage is, to put it mildly, unappealing. But the reality is that all water on Earth is recycled. Every drop of water you drink has been through the water cycle countless times and has, at some point in its history, been part of every conceivable process, including being waste. What modern water recycling technology does is compress this natural cycle into a controlled, engineered process. Advanced water treatment facilities can take treated wastewater and purify it to a standard that exceeds the quality of most traditional drinking water sources. The process typically involves microfiltration, reverse osmosis, and ultraviolet disinfection, producing water that is essentially free of contaminants. Several cities and regions around the world are already implementing direct or indirect potable reuse systems, and as water scarcity increases, this practice is expected to become much more widespread. The water coming out of these advanced treatment facilities is, by every scientific measure, clean and safe to drink. The only real barrier is psychological, and it is a significant one. Now here is something about water that connects to your heart, literally. Research has shown that staying well hydrated may reduce your risk of heart disease. A study published in the European Heart Journal in 2022, involving data from over 11,000 adults tracked over 25 years, found that people who consumed adequate amounts of water had significantly lower rates of heart failure than those who were chronically underhydrated. The mechanism is straightforward. When you are dehydrated, your blood becomes more concentrated. Your heart has to work harder to pump this thicker blood through your circulatory system. Over time, this increased workload can contribute to the thickening of the heart walls, a condition called left ventricular hypertrophy, which is a risk factor for heart failure. Simply staying well hydrated reduces this burden on the heart. It is one more reminder that something as simple as drinking enough water can have profound effects on your long-term health. Let us turn to a fact about water that is both poetic and scientifically profound. Every glass of water you drink is a connection to the stars. The hydrogen in water, the H in H2O, was created in the Big Bang, roughly 13.8 billion years ago. It is one of the first elements that formed as the universe expanded and cooled from its initial state of incomprehensible heat and density. The oxygen in water, the O in H2O, was forged in the nuclear furnaces of massive ancient stars that exploded as supernovae, scattering their newly created elements into the cosmos. These elements drifted through space for billions of years before coming together to form the solar system, the Earth, and eventually the water in your glass. When you drink water, you are literally consuming the products of stellar evolution. The hydrogen in your water is older than the stars. The oxygen was born in the death of a star. You are drinking the cosmos. Here is something that bridges the gap between water science and economics in a way that is often overlooked. Water is drastically underpriced in most of the world relative to its true value. Because water is essential for life, governments have historically subsidized water services to make them affordable for all citizens. The result is that the price consumers pay for water rarely reflects the full cost of sourcing, treating, and distributing it, let alone the environmental cost of using it. This underpricing leads to waste. When something is cheap, people tend to use more of it and value it less. The average person in a developed nation uses far more water than necessary, not because they need to, but because the low cost provides little incentive for conservation. Many water economists argue that more realistic pricing of water would encourage conservation, fund necessary infrastructure improvements, and help protect water resources for future generations. The challenge, of course, is ensuring that higher prices do not disproportionately burden low-income populations for whom affordable water is a matter of survival. And speaking of conservation, here is a fact that might make you rethink your daily habits. The average person in a developed nation uses between 80 and 100 gallons of water per day at home. That includes drinking, cooking, bathing, flushing toilets, doing laundry, washing dishes, and watering lawns. Of all these uses, drinking and cooking account for a tiny fraction, only about 2 to 3 gallons per day. The rest goes to activities that, while important, could be significantly reduced with simple behavioral changes and more efficient technologies. Low-flow showerheads, efficient toilets, front-loading washing machines, and drip irrigation systems can dramatically reduce household water use without any sacrifice in quality of life. Fixing a single leaky faucet that drips once per second can save over 3,000 gallons of water per year. Small changes multiplied across millions of households add up to enormous water savings. Let us now explore something that sounds counterintuitive. Drinking water can help you lose weight. This is not a gimmick or a fad diet claim. It is supported by scientific research. Several studies have shown that drinking water before meals can reduce the amount of food people eat during the meal, leading to reduced calorie intake and, over time, weight loss. One study found that adults who drank about 16 ounces of water before each meal lost significantly more weight over a 12-week period than those who did not. There are several reasons this works. First, water takes up space in the stomach, creating a sensation of fullness. Second, people often confuse thirst with hunger. When you feel what you think is a hunger pang, your body may actually be signaling thirst. Drinking water can satisfy this signal without adding any calories. Third, water has 0 calories, and replacing calorie-containing beverages like soda, juice, or sweetened coffee with water reduces overall calorie intake. It is one of the simplest, cheapest, and most effective weight management strategies available, and it requires no special equipment, no subscription, and no willpower beyond remembering to drink a glass of water before you eat. Here is something that very few people realize about the relationship between water and sleep. Dehydration can significantly impair your sleep quality. Research has found that people who are inadequately hydrated tend to have shorter sleep duration and less restful sleep than those who are well hydrated. A large cross-sectional study found that adults who slept only 6 hours per night had significantly higher rates of inadequate hydration compared to those who slept 8 hours. The relationship appears to be bidirectional. Dehydration impairs sleep, and poor sleep contributes to dehydration. This is partly because a hormone called vasopressin, which helps the body retain water, is released in a pulsatile fashion during sleep. If your sleep is cut short or disrupted, you may miss the later release of vasopressin, leading to greater water loss through urine production. The result is a vicious cycle where dehydration disrupts sleep, and disrupted sleep worsens dehydration. Ensuring adequate hydration throughout the day, while being careful not to drink too much right before bed, which could disrupt sleep with trips to the bathroom, is a simple way to support better sleep. Now, let us delve into something that sounds almost magical but is entirely real. Water has the remarkable ability to store and release energy on a massive scale, and human civilization has been harnessing this ability for centuries. Hydroelectric power, generating electricity from flowing water, is one of the oldest and most important sources of renewable energy in the world. The principle is straightforward. Water flowing from a higher elevation to a lower elevation carries kinetic energy, which can be captured by turbines and converted into electricity. Hydroelectric dams provide approximately 16% of the world's electricity, and in some countries, hydropower provides the vast majority of electrical energy. Unlike fossil fuel power plants, hydroelectric facilities produce no direct carbon emissions during operation. However, they do have significant environmental impacts, including disrupting river ecosystems, blocking fish migration, flooding large areas of land, and displacing communities. The relationship between water and energy is complex, and there is no perfect solution, but water's ability to store and release energy remains one of its most important properties for human civilization. Here is a fact about water that touches on the mystery of consciousness itself. Your brain, that extraordinary organ that produces your thoughts, memories, emotions, and sense of self, is about 75% water. When your brain loses even a small amount of its water content, its function measurably declines. Brain imaging studies have shown that dehydration can cause the brain to actually shrink slightly in volume, pulling away from the skull. When a dehydrated person is given water to drink, the brain plumps back up to its normal size. These changes in brain volume correlate with changes in cognitive performance. The thought you are having right now as you listen to these words is happening in a medium that is 3/4 water. Consciousness itself, as far as we understand it, is a process that takes place in water. Without water, there is no thought, there is no memory, there is no you. Let us take a moment to discuss something that connects water to culture, ritual, and spirituality. Throughout human history, water has been revered as sacred by virtually every culture on Earth. Water plays a central role in baptism in Christianity, symbolizing purification and rebirth. In Hinduism, the Ganges River is considered holy, and millions of people pilgrimage to bathe in its waters for spiritual cleansing. In Islam, ritual washing with water called wudu is performed before prayer. In Judaism, the mikveh, a ritual bath, is used for spiritual purification. Indigenous cultures around the world have their own traditions honoring water as sacred and essential. The universal reverence for water across cultures and throughout history reflects a deep, intuitive understanding of water's importance that modern science has confirmed and quantified. Water is not just a chemical compound. It is a substance that has shaped human culture, religion, and meaning-making for as long as humans have existed. And now, here is a fact about water and your immune system. Staying well hydrated supports your body's immune function in several important ways. Water helps produce lymph, the fluid that circulates through your lymphatic system, carrying white blood cells and other immune cells throughout your body. Without adequate water, lymph production decreases, and the movement of immune cells is impaired. Water also helps maintain the health of the mucous membranes in your nose, mouth, and throat, your body's first line of defense against airborne pathogens. When these membranes dry out due to dehydration, they become less effective at trapping and neutralizing bacteria and viruses before they can enter your body. Additionally, proper hydration supports kidney function, which is important for removing waste products and toxins from the blood, reducing the burden on the immune system. While drinking water will not prevent you from catching a cold or the flu, chronic dehydration can weaken your body's defenses and make you more susceptible to infections. Here's something that connects water to the world of sports and athletic performance in a dramatic way. Even a 2% decrease in body hydration can result in a noticeable decline in athletic performance. For a 150-pound athlete, that is only about 1.5 pounds of water loss, easily achievable through sweating during a single workout. At this level of dehydration, endurance performance can drop by as much as 10 to 20%. At 3 to 4% dehydration, muscular strength and power output decrease significantly. At 5% and above, the risk of heat-related illness increases dramatically, and performance can decline by as much as 30%. Many elite athletes meticulously monitor their hydration status, weighing themselves before and after training sessions to calculate exactly how much water they have lost through sweat and replacing it precisely. For the average person who exercises regularly, the lesson is simpler but equally important. Drink water before, during, and after exercise. Your performance and your safety depend on it. Let us end this first section with a thought that brings everything together. Water is the most common substance on the surface of our planet, and yet it is one of the most remarkable, most unusual, and most important substances in the known universe. It shapes our bodies, our health, our agriculture, our energy systems, our cities, our cultures, and our very survival. It connects us to every living thing on Earth and to the ancient stars from which its elements were forged. It is at once utterly ordinary and profoundly extraordinary, and every single day it flows through your life in ways you have barely begun to appreciate. There is so much more to discover. The story of water is far from over. In the next part of this documentary, we will dive even deeper into the surprising, the unsettling, and the awe-inspiring world of drinking water. We will explore how water affects your brain in ways you never imagined, how ancient civilizations engineered water systems that still inspire wonder, how climate change is reshaping the future of water on this planet, and dozens more facts that will leave you looking at your glass of water with entirely new eyes. The water in your glass is not just a drink, it is a story billions of years old, a story that is still being written with every drop. Welcome back. If you were with us for the first part of this journey, you already know that the glass of water sitting in front of you is far more complex, far more ancient, and far more important than you ever imagined. But we have only scratched the surface. The story of drinking water goes deeper, into the hidden chemistry of your cells, into the engineering marvels of ancient civilizations, into the uncertain future that climate change is writing for every water source on the planet. There are truths about water that will unsettle you. There are facts that will astonish you. And there are revelations that may very well change the decisions you make tomorrow morning when you reach for your first drink of the day. So settle in, because the second half of this journey is about to begin, and the water in your glass has more secrets to tell. Let us begin this section with something that affects nearly every person on the planet, yet almost nobody talks about. The pipes that carry water to your home are, in many places, extraordinarily old. In cities around the world, the underground water distribution infrastructure, the network of pipes that connects treatment plants to homes and businesses, was installed decades ago, and in some cases, well over a century ago. Cast iron pipes installed in the late 1800s and early 1900s are still in active use in many urban areas. These aging pipes corrode over time, developing cracks, leaks, and internal buildup that can affect both the quality and the pressure of the water they deliver. It has been estimated that aging water infrastructure in developed nations loses billions of gallons of treated, clean drinking water every year through leaks alone. That is water that has already been through the expensive process of treatment and purification, lost before it ever reaches a faucet. In some cities, water main breaks are a regular occurrence, disrupting service and sometimes contaminating the water supply with soil, bacteria, and other substances that enter through the breach. The infrastructure that delivers your clean water is, in many places, crumbling, and replacing it is one of the most expensive and disruptive public works challenges imaginable. Connected to that aging infrastructure is a problem that has made international headlines and shattered public trust: lead contamination from old pipes. We touched on this briefly in the first part, but the full scope of the issue deserves deeper examination. Lead was commonly used in water service lines, the pipes connecting the main water line in the street to individual homes, for decades. Lead solder was also used to join copper pipes in household plumbing well into the 1980s. When the chemistry of the water flowing through these pipes changes, due to shifts in the water source, changes in treatment chemicals, or fluctuations in pH, the protective mineral coating inside lead pipes can break down, releasing lead directly into the drinking water. This is exactly what happened in the infamous water crisis in Flint, Michigan, where a change in water source corroded the lead service lines and exposed over 100,000 residents to dangerous levels of lead. But Flint is not an isolated case. Testing has revealed elevated lead levels in the drinking water of schools, homes, and public buildings in communities around the world. The full extent of lead contamination in drinking water is still being uncovered, and the health consequences, particularly for children, whose developing brains are exquisitely vulnerable to lead's neurotoxic effects, are devastating and irreversible. Now let us shift to something that might change the way you think about a very common beverage choice: sparkling water. Carbonated water, seltzer, sparkling water, whatever you call it, has surged in popularity in recent years as people look for alternatives to sugary sodas. But is sparkling water as healthy as still water? The carbonation in sparkling water is created by dissolving carbon dioxide gas under pressure, which forms carbonic acid. This makes sparkling water slightly more acidic than still water, with a pH typically between 3 and 4, compared to still water's neutral pH of around 7. This has led to concerns that sparkling water might erode tooth enamel or harm bone density. However, the research is reassuring on both counts. While sparkling water is indeed more acidic than still water, its acidity is far lower than that of sodas, fruit juices, or other acidic beverages, and studies have found that its effect on tooth enamel is minimal, far less than the effect of drinking orange juice, for example. As for bone health, a large study found no association between sparkling water consumption and decreased bone density. The only carbonated beverage associated with lower bone density was cola, likely because of its phosphoric acid content rather than the carbonation itself. So sparkling water on its own without added sugars or artificial sweeteners is essentially equivalent to still water for hydration purposes. If it helps you drink more water overall, it is a perfectly healthy choice. Here is a fact that takes us back millions of years and deep underground. Some of the water on Earth has been trapped underground for extraordinarily long periods of time. Scientists have discovered pockets of water deep within the Earth's crust that have been isolated from the surface for millions, even billions of years. In a mine in Ontario, Canada, researchers found water trapped in rock that was determined to be approximately 2 billion years old, making it some of the oldest water ever discovered on Earth. This ancient water had a completely different chemical composition from surface water, rich in dissolved gases and minerals accumulated over geological time. Remarkably, the researchers also found evidence that this ancient water could potentially support microbial life, even after being cut off from sunlight and the surface for eons. These discoveries have profound implications for our understanding of where life can exist, not just on Earth, but potentially on other planets and moons where ancient water might be trapped beneath the surface. And speaking of water hidden beneath the surface, let us talk about something that most people have never heard of, but that represents one of the largest reserves of water on the planet: deep groundwater. While most people are familiar with the concept of shallow aquifers, the underground water sources that wells tap into, there is an enormous amount of water stored much deeper in the Earth's crust, at depths of 1 to 10 kilometers or more. A study published in the journal Nature Geoscience estimated that there are approximately 23 million cubic kilometers of groundwater in the upper 2 kilometers of the Earth's crust alone. To put that in perspective, that is roughly 100 times the volume of all the surface freshwater in every lake, river, and stream on the planet combined. Much of this deep groundwater is very old, thousands to millions of years old, and in many cases it is too deep, too salty, or too contaminated with naturally occurring minerals to be used for drinking without extensive treatment. But its existence reminds us that the water story of our planet extends far beneath our feet, into hidden reservoirs that we are only beginning to understand. Now let us explore a topic that is increasingly relevant in a warming world: the relationship between climate change and drinking water. Climate change is fundamentally altering the water cycle in ways that are already being felt around the globe. As the atmosphere warms, it can hold more moisture, approximately 7% more for every degree Celsius of warming. This means that when it does rain, the rainfall tends to be heavier and more intense. At the same time, warmer temperatures increase evaporation from soil and water surfaces, which can intensify droughts in regions that are already dry. The result is a paradox: more intense rainfall events leading to more flooding, alongside longer and more severe droughts. Both extremes are terrible for drinking water supplies. Floods can overwhelm water treatment systems, wash contaminants into water sources, and damage infrastructure. Droughts deplete reservoirs, lower groundwater levels, concentrate pollutants in diminished water sources, and can leave communities without adequate water. Climate models project that these trends will intensify in the coming decades, putting drinking water supplies for billions of people at increased risk. The water crisis is not just a future possibility, it is a present reality that climate change is accelerating. Here is another dimension of the climate-water connection that most people do not think about. As glaciers and ice sheets melt due to rising temperatures, the water they contain flows into the ocean, where it becomes salt water, effectively lost as a freshwater resource. Glaciers serve as natural water storage systems, accumulating snow during cold periods and releasing meltwater during warm periods, providing a steady supply of fresh water to rivers and communities downstream. Hundreds of millions of people around the world depend on glacial meltwater for their drinking water supply, particularly in South Asia, Central Asia, and South America. As these glaciers shrink, and many are shrinking at unprecedented rates, the communities that depend on them face an existential threat. In the short term, accelerated melting may actually increase water availability as more meltwater flows downstream. But in the long term, as the glaciers disappear entirely, that water source will be gone. It is like living off a savings account. The withdrawals feel fine until the account is empty. Let us move from the global scale to the deeply personal once more. Here is a fact about water that most expectant parents are never told. The water a pregnant woman drinks is critically important not just for her own health, but for the development of her baby. The amniotic fluid that surrounds and protects a developing fetus is almost entirely water. This fluid cushions the baby against physical impact, maintains a stable temperature, allows the baby to move and develop muscles and bones, and supports the development of the lungs and digestive system. A pregnant woman's blood volume increases by approximately 50% during pregnancy to support the growing fetus, and maintaining this increased blood volume requires significantly more water intake. Dehydration during pregnancy has been associated with complications including neural tube defects, low amniotic fluid, preterm labor, and inadequate breast milk production after delivery. The quality of the water matters too. Exposure to contaminants like lead, certain pesticides, and disinfection byproducts during pregnancy has been linked in some studies to adverse birth outcomes. For a pregnant woman, every glass of water she drinks is directly nourishing and protecting the developing life inside her. Here is something that sounds almost too strange to be true, but it is well-documented science. Water can exist in a state that is neither fully liquid nor fully solid, a kind of in-between state called supercooled water. Under certain conditions, water can be cooled below its freezing point, below 0 degrees Celsius, without actually turning into ice. This happens when the water is very pure and undisturbed, with no nucleation sites, tiny particles, or surface irregularities, around which ice crystals can begin to form. Supercooled water can remain liquid at temperatures as low as -48 degrees Celsius under laboratory conditions, but it is in an extremely unstable state. The slightest disturbance, a vibration, a speck of dust, even a sudden jarring movement, can trigger instantaneous crystallization, and the entire volume of water freezes almost instantly. You can actually observe this phenomenon at home under certain conditions. Put a bottle of very pure water in the freezer, and if conditions are right, it will remain liquid even below freezing. Then give it a sharp tap or pour it onto a piece of ice and watch it freeze before your eyes. It is one of the most visually dramatic demonstrations of water's unusual physical properties. And while we are on the subject of water's unusual behaviors, here is another one that continues to puzzle scientists. Hot water can, under certain conditions, freeze faster than cold water. This counterintuitive phenomenon is known as the Mpemba effect, named after Erasto Mpemba, a Tanzanian student who observed it in the 1960s while making ice cream. When he pointed out to his teacher that hot milk froze faster than cold milk, he was initially laughed at, but subsequent experiments have confirmed that the effect is real, at least under certain conditions. Scientists have proposed various explanations, including differences in evaporation rates, dissolved gas content, convection currents, and the effect of supercooling, but no single explanation has been universally accepted. The Mpemba effect remains one of the most enduring mysteries in the physics of water, a humbling reminder that even something as common as water still holds secrets that science has not fully unraveled. Now let us discuss a topic that has generated enormous controversy and enormous profits: alkaline water. Alkaline water has a higher pH than regular drinking water, typically between 8 and 9, compared to regular water's neutral pH of about 7. Proponents claim that drinking alkaline water can neutralize acid in the body, slow aging, prevent cancer, boost energy, and provide a host of other health benefits. These claims have driven a multi-billion-dollar industry of alkaline water products, ionizer machines, and supplements. But what does the science actually say? The human body maintains its blood pH within an extremely narrow range, between 7.35 and 7.45, through powerful buffering systems involving the lungs, kidneys, and blood chemistry. Drinking alkaline water does not significantly change your blood pH because these buffering systems neutralize the alkalinity almost immediately. Your stomach, which maintains a strongly acidic environment with a pH between 1.5 and 3.5, will neutralize alkaline water as soon as it arrives. There is very little credible scientific evidence that drinking alkaline water provides any health benefits beyond basic hydration. The few studies that have suggested benefits were small, often poorly designed, or conducted in laboratory settings rather than in living humans. For the vast majority of people, the pH of their drinking water matters far less than the amount they drink and the contaminants it contains. Here's a related point about another water trend: distilled water. Distilled water is water that has been boiled into steam and then condensed back into liquid, leaving behind virtually all contaminants, minerals, and impurities. It is as close to pure H2O as you can practically get. Some people drink distilled water because they want to avoid any possible contaminants in their water supply. However, there are reasons to be cautious about making distilled water your sole source of hydration. Because distilled water contains no dissolved minerals, it is slightly aggressive chemically. It tends to absorb carbon dioxide from the air, forming a mild carbonic acid, and it can leach minerals from whatever it contacts, including your body. Some studies have suggested that long-term consumption of demineralized water can contribute to mineral deficiency and has been associated with increased risk of certain health problems, though the evidence is not conclusive. The World Health Organization has noted that water depleted in calcium and magnesium may be associated with cardiovascular risks. For occasional use, distilled water is perfectly fine. But for long-term, everyday drinking water, most health experts recommend water that retains some of its natural mineral content. Let us now explore a fact about water that is both fascinating and potentially life-saving. The temperature of water you drink can affect how quickly your body absorbs it. Research has shown that water at cooler temperatures, around 5 to 10 degrees Celsius, or roughly 40 to 50 degrees Fahrenheit, is absorbed more quickly by the body than water at room temperature or warm water. This is partly because cool water moves more rapidly from the stomach into the small intestine, where the majority of absorption takes place. For athletes or people at risk of dehydration, this means that drinking cool water during exercise or in hot conditions can be more effective at maintaining hydration than drinking warm water. However, the differences are relatively modest, and the most important factor by far is simply that you drink enough water, regardless of its temperature. If warm water is all that is available, or if you prefer warm water, drinking it is vastly better than drinking nothing. Here is a fact about water treatment that would probably disturb most people if they thought about it carefully. The water treatment process used by most municipal water systems was designed primarily to deal with the contaminants that were known and understood in the early to mid-20th century: bacteria, viruses, parasites, and common chemical pollutants. These treatment processes are very effective at what they were designed to do. But the chemical landscape of modern life has changed dramatically since these systems were designed. There are now tens of thousands of synthetic chemicals in use in industry, agriculture, and consumer products, and new ones are introduced every year. Many of these chemicals can find their way into water sources through industrial discharges, agricultural runoff, and consumer waste. A category of particular concern is PFAS, per and polyfluoroalkyl substances, sometimes called forever chemicals because they are extraordinarily resistant to environmental breakdown. PFAS are used in non-stick cookware, waterproof clothing, food packaging, firefighting foams, and many other products. They have been detected in drinking water supplies around the world, and studies have linked PFAS exposure to a range of health effects including certain cancers, thyroid disease, immune system suppression, and reproductive problems. Conventional water treatment does not effectively remove PFAS. Specialized technologies like granular activated carbon, ion exchange, and high-pressure membrane systems can remove them, but many treatment facilities do not yet have this capability. You may be drinking PFAS-contaminated water right now and not know it, because many water systems have not yet been tested for these chemicals. And this brings us to a broader point about water testing and transparency. In many countries, water utilities are required to test their water for specific contaminants and publish the results in annual water quality reports, sometimes called consumer confidence reports. These reports are typically available online or by request, and they contain detailed information about what is in your water and whether it meets regulatory standards. Yet studies have found that the vast majority of consumers never read these reports and have no idea what is in their water. This is partly a communication problem. The reports are often dense, technical documents that are difficult for non-experts to understand, but it is also a complacency problem. When clean water flows reliably from the tap, there is little motivation to question its quality. Yet as we have discussed, meeting regulatory standards does not necessarily mean free of all contaminants. Regulatory standards are often set based on balancing health risks against economic feasibility, and they may not reflect the latest scientific understanding of what is safe. Emerging contaminants like PFAS, microplastics, and pharmaceutical residues may not even be covered by existing standards. Being an informed consumer of your own drinking water, knowing its source, reading the quality reports, understanding what your local treatment process does and does not remove, is one of the most important things you can do for your health and your family's health. Let us now step into a realm where water meets cutting-edge technology. Around the world, scientists and engineers are developing revolutionary new approaches to water purification that could transform access to clean drinking water. One of the most promising is the use of graphene oxide membranes. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, is the thinnest, strongest material ever discovered. When formed into a membrane, graphene oxide can filter out salt, heavy metals, organic molecules, and even bacteria from water with remarkable efficiency and at lower pressures than conventional reverse osmosis membranes. This means less energy is required, which could make desalination and advanced water purification far more affordable. Other innovations include solar-powered desalination devices that can produce clean water from seawater using only sunlight, bio-inspired water purification systems that mimic the way certain plants and organisms filter water, and nanotechnology-based filters that can target and remove specific contaminants at the molecular level. These technologies are still being refined and scaled up, but they offer hope that the water challenges of the 21st century can be met with human ingenuity. Here is another technological development that is already providing drinking water in some of the most water-scarce regions on Earth: fog collection. In certain coastal and mountainous areas, fog is a reliable source of atmospheric moisture even when rain is scarce. Fog collectors are large mesh screens, typically made of polyethylene or polypropylene, that are erected in foggy areas. As fog passes through the mesh, tiny water droplets collect on the fibers, merge together, and drip down into collection troughs. The collected water is then channeled into storage tanks. In some locations, a single fog collector can harvest several hundred liters of water per day. Communities in Chile, Peru, Morocco, and other countries have successfully implemented fog collection systems to supplement their water supplies. It is an elegant, low-technology solution that takes advantage of a natural phenomenon to provide drinking water where conventional sources are limited. The idea that you can literally pull water out of thin air is remarkable, and it is happening right now. Similarly, atmospheric water generators are devices that extract water from humid air using either cooling condensation or desiccant technology. In cooling-based systems, the air is drawn over a cold surface, causing the moisture in the air to condense into liquid water, which is then collected and filtered. It works on the same principle as the condensation that forms on the outside of a cold glass on a humid day. These devices range from small units that can produce a few liters per day for household use to large industrial units capable of producing thousands of liters per day. While the technology is energy-intensive and not yet economically competitive with conventional water sources in most areas, it has significant potential for emergency relief situations, military operations, and isolated communities without access to traditional water infrastructure. The ability to generate drinking water from the air wherever you are is a concept that would have seemed like science fiction a few decades ago, but it is now a commercially available reality. Now let us return to the human body and explore something that many people struggle with: how to tell if you are properly hydrated. We discussed earlier that thirst is not an early warning system. By the time you feel thirsty, you are already dehydrated. So what is a better indicator? One of the simplest and most reliable methods is to check the color of your urine. Well-hydrated urine should be a pale, straw-like yellow, light enough to be nearly clear, but with a slight yellow tint from a pigment called urochrome. If your urine is dark yellow or amber, you are likely dehydrated and should drink more water. If your urine is completely colorless, you may be overhydrating. There are some caveats. Certain foods like beets and asparagus can change urine color. Certain medications can alter its appearance, and B vitamins can turn urine a bright, almost fluorescent yellow regardless of hydration status. But as a general daily guide, the color of your urine is one of the best indicators you have of your hydration status. It is free, it is always available, and it is remarkably accurate. Here is a fact about water and aging that most people find both sobering and motivating. As we age, our body's water content decreases, and our sense of thirst becomes less reliable. Older adults are significantly more vulnerable to dehydration than younger adults for several reasons. First, the total body water content declines with age, from approximately 75% in infants to as low as 50% in elderly adults. Second, the kidneys become less efficient at concentrating urine, leading to greater water loss. Third, and perhaps most critically, the thirst mechanism becomes blunted with age. Older adults simply do not feel as thirsty as younger adults even when their bodies need water. This means they are less likely to drink enough to maintain proper hydration. The consequences can be severe. Dehydration in the elderly is associated with increased risk of urinary tract infections, kidney stones, falls, confusion, delirium, hospital admission, and even death. It is one of the most common and most preventable causes of illness in older adults. If you have elderly family members, encouraging and reminding them to drink water regularly, rather than waiting until they feel thirsty, is one of the most important things you can do for their health. Let us now talk about something that bridges the gap between water science and daily habit: the water you give to your children. Children's water needs are different from adults, and getting them right is more important than many parents realize. Children have higher metabolic rates than adults, meaning they produce more metabolic waste that must be flushed out by the kidneys. They also have a larger body surface area relative to their mass, which means they lose more water through the skin. And they are often less attentive to thirst cues, particularly when they are absorbed in play or activities. Chronic mild dehydration in children has been associated with reduced cognitive performance, including impaired attention, memory, and visual motor skills. Several studies conducted in school settings have found that providing children with access to water during the school day improved their performance on cognitive tests. One study found that children who drank water before taking a test performed significantly better than those who did not. Ensuring that children drink adequate water throughout the day, not just at meal times, is a simple intervention that can support their learning, behavior, and overall health. Here's a fact about water that many people find surprising and somewhat unsettling. Your body produces water internally as a byproduct of metabolism. When your cells break down glucose and other nutrients for energy through cellular respiration, one of the products of that chemical reaction is water. This is called metabolic water, and your body produces approximately 300 milliliters of it per day, roughly 1¼ cups, through normal metabolic processes. While this is not nearly enough to meet your total water needs, it is a meaningful contribution. Some desert-adapted animals, like the kangaroo rat, have evolved to survive almost entirely on metabolic water, rarely or never needing to drink liquid water at all. Their kidneys are extraordinarily efficient, their behavior minimizes water loss, and they obtain sufficient water from the metabolic breakdown of the dry seeds they eat. Humans cannot do this. Our water needs far exceed what metabolism alone can provide, but the fact that your body creates water as a byproduct of burning calories is a remarkable piece of biology that most people have never heard of. Now let us explore a dimension of water that is often overlooked but critically important: water and food safety. Water is intimately connected to the safety of the food supply. Contaminated water used to irrigate crops can transfer pathogens, heavy metals, and chemical residues to fruits and vegetables. Outbreaks of foodborne illness have been traced to produce that was irrigated with water contaminated by animal waste or human sewage. Washing produce with contaminated water does not remove contaminants, it adds them. The water used in food processing facilities must meet strict quality standards because contaminated processed water can introduce pathogens into otherwise safe food products. Ice made from contaminated water can transmit disease just as effectively as drinking the water directly. Even the water used to wash hands during food preparation matters. Inadequate hand-washing with contaminated water is one of the most common pathways for foodborne illness transmission worldwide. The safety of your food is, in many ways, only as good as the safety of the water used to grow, process, and prepare it. Here is something that connects water to one of the most mundane yet essential parts of daily life: your morning cup of coffee or tea. Both coffee and tea are predominantly water. A cup of brewed coffee is about 98 to 99% water, and tea is similar. This means that the quality of the water you use to brew your coffee or tea has a direct and significant impact on its taste. If your water has a strong chlorine taste, your coffee will have a chlorine taste. If your water is very hard, the excess minerals will interact with the compounds in coffee and tea in ways that alter the flavor, often making it bitter, chalky, or flat. If your water is very soft or highly purified, the coffee may taste weak or sour because there are not enough minerals to properly extract the flavorful compounds from the grounds. This is why specialty coffee shops invest in sophisticated water filtration systems. The ideal water for coffee brewing, according to the Specialty Coffee Association, should have a total dissolved solids content of approximately 150 parts per million, a calcium hardness of about 50 to 75 parts per million, and a neutral to slightly alkaline pH for tea. The requirements are similar, though some tea experts prefer slightly softer water for delicate teas like white and green teas. The point is this: if you care about the taste of your coffee or tea, you should care about the quality of your water, because water is the dominant ingredient. Let us now discuss a phenomenon that is reshaping water resources around the world: the privatization of water. Throughout most of history, water has been treated as a public resource, managed by governments and provided to citizens as a basic service. But over the past several decades, there has been a growing trend toward privatization, turning the management and, in some cases, the ownership of water systems over to private companies. Proponents argue that private companies can manage water systems more efficiently, invest in necessary infrastructure upgrades, and provide better service. Critics argue that privatization turns a basic human right into a commodity, leading to higher prices, reduced access for the poor, and a focus on profit over public health. The debate has played out in communities around the world, sometimes peacefully and sometimes in outright conflict. In Cochabamba, Bolivia, the privatization of the water system in 2000 led to massive price increases that triggered widespread protests known as the Cochabamba Water War, ultimately resulting in the reversal of the privatization. The fundamental question at the heart of this debate is one that humanity has not yet fully resolved. Is water a human right that should be accessible to all, or is it an economic good that should be priced and managed according to market principles? The answer has profound implications for billions of people. Here is a fact that connects water to a completely different aspect of human experience: creativity and problem solving. You may have noticed that some of your best ideas come to you in the shower. This is not a coincidence, and it is partly related to water. The experience of warm water flowing over your body is physically relaxing, which reduces the stress hormone cortisol and allows your brain to shift from a focused, analytical mode to a more relaxed, diffuse mode of thinking. This diffuse mode of thinking is associated with greater creativity, insight, and the ability to make unexpected connections between ideas. The white noise of running water also provides a mild level of sensory stimulation that is not demanding enough to distract you, but is sufficient to prevent your mind from becoming completely idle. Additionally, the warmth and sensory pleasure of water can trigger the release of dopamine, the neurotransmitter associated with reward and motivation, which further facilitates creative thinking. While this is not strictly about drinking water, it underscores the deep and multifaceted relationship between water and human cognition. Now let us return to the chemistry of drinking water for a fact that is immediately practical. The pH of your drinking water matters more than you might think, though not for the reasons that alkaline water marketers would have you believe. While drinking slightly alkaline water does not provide magical health benefits, drinking water that is too acidic can be genuinely problematic. Acidic water with a pH below 6.5 is corrosive. It can leach metals like lead, copper, zinc, and iron from your plumbing, increasing your exposure to these substances. This is one of the reasons that water treatment plants carefully monitor and adjust the pH of treated water before sending it into the distribution system. The addition of lime or soda ash can raise the pH to a level that is less corrosive to pipes, providing a protective layer of mineral deposit inside the pipes that acts as a barrier between the water and the pipe material. If you have a private well, testing your water's pH is particularly important because there is no municipal treatment process doing this for you. Acidic well water is more common than many people realize, particularly in areas with certain types of bedrock, and it can silently expose you and your family to elevated levels of dissolved metals. Let us explore the remarkable world of water and DNA. Water is not just the medium in which DNA exists, it is an active participant in the structure and function of your genetic material. The double helix structure of DNA depends on water molecules for its stability. Water molecules form hydrogen bonds with the base pairs inside the helix and with the phosphate groups on the outside, holding the structure together. The major and minor grooves of the DNA helix contain ordered water molecules that are integral to the molecule's shape. Enzymes that read, copy, and repair DNA require water to function. The process of DNA replication, which happens every time a cell divides, involves water molecules at every step. Proteins that interact with DNA recognize specific patterns of water molecules on the surface of the helix, and these water patterns help determine which genes are turned on or off. At the most fundamental level, the instruction manual for building and maintaining your body, your genetic code, depends on water for its very existence. Without water, there is no DNA. Without DNA, there is no life. The partnership between water and genetics is absolute and unbreakable. Here is a fact about water that touches on history and engineering in equal measure. The ancient Romans were justly famous for their aqueducts, but they were not the only ancient civilization to develop remarkable water infrastructure. The Nabateans, who built the legendary city of Petra in what is now Jordan, were masters of water engineering in one of the most arid environments on Earth. They built an intricate network of channels, cisterns, dams, and ceramic pipes that captured, stored, and distributed water throughout their desert city, supporting a population of perhaps 30,000 people in a region that receives less than 6 inches of rain per year. The ancient Persians developed qanats, gently sloping underground channels that used gravity to transport water from highland aquifers to lowland communities over distances of many kilometers, sometimes tens of kilometers. Some of these qanats are still in use today, over 2,000 years after they were built. The Sinhalese civilization of ancient Sri Lanka constructed massive artificial reservoirs and an interconnected irrigation network that was, at the time, the most complex water management system in the world. These ancient engineers understood something fundamental. Water is life, and the ability to capture, store, and distribute water is the foundation of civilization. Their ingenuity continues to inspire modern water engineers facing similar challenges in arid and water-stressed regions. Let us talk about a topic that affects the daily experience of hundreds of millions of people: the taste and smell of tap water. Even when tap water is perfectly safe to drink, it can sometimes taste or smell unpleasant, and the reasons are varied and sometimes surprising. A musty, earthy taste or smell in tap water is often caused by naturally occurring organic compounds produced by algae and bacteria in the water source, particularly compounds called geosmin and 2-methylisoborneol. These compounds are harmless but can make water taste and smell like dirt or mold, even at concentrations so low they are measured in parts per trillion. Humans are extraordinarily sensitive to these compounds. We can detect geosmin at concentrations as low as 5 parts per trillion, which is equivalent to about 1 teaspoon in 200 Olympic-sized swimming pools. A metallic taste is often caused by iron, manganese, or copper in the water, either from the source or from pipes. A rotten egg smell is typically caused by hydrogen sulfide gas, which can be produced by bacteria in the water source or in the pipes. A bleach-like taste or smell is caused by chlorine. Each of these issues has specific causes and solutions, and in most cases the water is still safe to drink despite the unpleasant taste or odor. But taste and smell are powerful determinants of behavior. If tap water does not taste good, people are less likely to drink it and more likely to turn to bottled water or sugary beverages, with all the associated health and environmental consequences. Here is a fact that connects water to the future in a way that is both exciting and sobering. Water scarcity is projected to become one of the defining challenges of the 21st century. The United Nations estimates that by 2025, roughly 1.8 billion people will be living in areas with absolute water scarcity, and 2/3 of the world's population could be living under water-stressed conditions. By 2050, global water demand is projected to increase by 20 to 30% above current levels, driven by population growth, urbanization, economic development, and changing consumption patterns. At the same time, climate change is altering precipitation patterns, reducing snowpack and glacier storage, and increasing the frequency and severity of droughts. The gap between water demand and water supply is widening, and closing that gap will require massive investment in water infrastructure, aggressive conservation efforts, widespread adoption of water-efficient technologies, and fundamental changes in how we value and manage water as a resource. The water crisis is not a distant, abstract threat. It is happening now in communities around the world, and its impacts fall disproportionately on the poorest and most vulnerable populations. Let us now discuss something that is simultaneously commonplace and extraordinary: what happens when water boils. When you heat water on your stove, you are adding energy to the water molecules, causing them to move faster and faster. As the temperature approaches 100 degrees Celsius, 212 degrees Fahrenheit, at sea level, the water molecules have enough energy to break free from the liquid entirely and escape as gas or steam. But here is what is remarkable. During the actual boiling process, the temperature of the water does not continue to rise. Even if you turn the heat up higher, the water remains at 100 degrees Celsius until it has all been converted to steam. All the extra energy goes into breaking the hydrogen bonds between water molecules, the energy of the phase change, rather than raising the temperature. This is why water is such an effective medium for cooking. It provides a stable temperature environment. It is also why steam burns are so dangerous. When steam condenses on your skin, it releases the enormous amount of energy that was stored in the phase change, transferring far more heat to your skin than boiling water alone would. And here is a related fact that is immediately practical for anyone who has ever boiled water for drinking safety. Boiling water is one of the oldest and most effective methods of making water safe to drink. Bringing water to a rolling boil for at least 1 minute or 3 minutes at elevations above 2,000 meters, where the lower atmospheric pressure means water boils at a lower temperature, kills or inactivates virtually all disease-causing organisms, including bacteria, viruses, and parasites. Boiling does not remove chemical contaminants, heavy metals, or dissolved solids, but for biological contamination, which is responsible for the vast majority of waterborne diseases worldwide, boiling is remarkably effective. It requires no special equipment, no chemicals, and no technical expertise. In emergency situations, natural disasters, and communities without access to water treatment infrastructure, boiling remains one of the most important tools for preventing waterborne illness. It has saved countless millions of lives over the centuries. Another method of water purification that is gaining increasing attention is ultraviolet, or UV, disinfection. UV light at specific wavelengths, particularly around 254 nanometers, damages the DNA of microorganisms, rendering them unable to reproduce and effectively killing them. UV disinfection is used in both large-scale water treatment plants and in small, portable devices designed for individual use. Unlike chlorine, UV treatment does not add any chemicals to the water, does not alter its taste or smell, and does not produce harmful byproducts. However, it does have limitations. UV light must be able to penetrate the water to reach the microorganisms, so it is less effective in turbid or cloudy water. It also provides no residual disinfection. Once the water leaves the UV treatment zone, it is no longer being protected against recontamination. Despite these limitations, UV disinfection is becoming increasingly popular as a complement to other treatment methods, particularly in situations where chemical treatment is undesirable or impractical. Let us now turn to a fact about water that affects your daily comfort in ways you might not have connected to hydration. Dehydration is one of the most common and most overlooked causes of headaches. While headaches can have many causes — tension, stress, eye strain, hormonal changes, medical conditions — dehydration headaches are remarkably common and remarkably easy to treat. When you are dehydrated, your brain can temporarily shrink slightly in volume due to fluid loss, pulling away from the skull and triggering pain receptors in the surrounding membranes. Dehydration also reduces blood volume, which can decrease the flow of blood and oxygen to the brain, contributing to headache pain. Many people who suffer from frequent headaches have found significant relief simply by increasing their water intake. Before reaching for pain medication the next time you feel a headache coming on, try drinking a tall glass of water and waiting 20 to 30 minutes. In many cases, that simple intervention is all that is needed. Here is something that connects water to an experience nearly every adult has had: the hangover. Alcohol is a diuretic. It suppresses the production of antidiuretic hormone, causing your kidneys to produce more urine and leading to increased water loss. A night of heavy drinking can result in significant dehydration, which is a major contributor to hangover symptoms including headache, fatigue, dry mouth, dizziness, and nausea. Studies have shown that alternating alcoholic drinks with glasses of water and drinking a large glass of water before going to bed after drinking can significantly reduce the severity of hangover symptoms. The dehydration caused by alcohol also contributes to the characteristic brain fog and difficulty concentrating that accompanies a hangover, the same cognitive effects we discussed earlier in the context of general dehydration. While dehydration is not the only cause of hangovers, alcohol also causes inflammation, disrupts sleep architecture, and irritates the stomach lining. It is one of the most significant and most easily addressable contributing factors. The simplest hangover prevention strategy in the world is free and available from any tap: drink more water. Now let us discuss a topic that has significant implications for public health: water and diabetes. Research has uncovered an interesting relationship between water intake and the risk of developing type 2 diabetes. Several large epidemiological studies have found that people who drink more water have a lower risk of developing high blood sugar and type 2 diabetes. One proposed mechanism involves vasopressin, the antidiuretic hormone we discussed earlier. When you are dehydrated, your body produces more vasopressin to conserve water. Vasopressin has been shown to stimulate the liver to produce more glucose and to increase the production of a stress hormone called cortisol, which also raises blood sugar. Chronic dehydration could therefore lead to chronically elevated blood sugar levels over time, increasing the risk of insulin resistance and eventually diabetes. While the relationship is not as simple as drink more water to prevent diabetes, the evidence suggests that adequate hydration is one of many lifestyle factors that can influence metabolic health. Given the enormous and growing global burden of type 2 diabetes, even a small protective effect from increased water intake could have significant public health implications. Here is a fact about water and the ocean that loops back to drinking water in a surprising way. The ocean is the ultimate source of most of the fresh water on Earth. Through the water cycle, the sun evaporates water from the ocean's surface, effectively desalinating it, and this water vapor rises, forms clouds, and eventually falls as freshwater precipitation over land. The ocean is, in effect, the world's largest natural desalination plant. Every river, every lake, every underground aquifer is ultimately fed by fresh water that originated as evaporation from the ocean. The entire freshwater supply on which human civilization depends is a gift from the interplay between the sun and the sea. But human activities are altering this natural system. Pollution of the oceans with plastics, chemicals, and excess nutrients affects the quality of the water that evaporates. Climate change is shifting precipitation patterns, bringing more rain to some areas and less to others, often in ways that do not align with where human populations need the water most. The health of the ocean and the health of our drinking water supply are deeply connected, even though they might seem like separate issues. Let us now explore something that takes us to the very frontier of water science, the fourth phase of water. We all learned in school that water has 3 phases: solid, liquid, and gas. But research by Gerald Pollack at the University of Washington has proposed the existence of a 4th phase of water, called exclusion zone water, or EZ water. When water is in contact with certain hydrophilic surfaces, It forms a layer of structured water that has different properties from bulk liquid water. This exclusion zone water has a higher viscosity, a slightly negative charge, and a different molecular arrangement than ordinary liquid water. It excludes solutes and particles, hence the name exclusion zone. While this research is still considered somewhat controversial and is not universally accepted in the scientific community, it has opened up fascinating new questions about the nature of water and its behavior in biological systems, where water is always in contact with surfaces, cell membranes, proteins, DNA. If easy water turns out to be as significant as Pollack and his colleagues believe, it could change our understanding of how water functions inside living cells and how it interacts with biological molecules. Here's a fact that will make you think about water in an entirely new way. The amount of water on Earth is essentially fixed. It has not significantly increased or decreased in billions of years. The water cycle moves water between the atmosphere, the surface, and underground, but it does not create new water or destroy old water. The Earth is essentially a closed system when it comes to water. A tiny amount is lost to space over geological time through a process called hydrogen escape, and a tiny amount is added through volcanic activity and incoming comets and meteorites, but these amounts are negligible compared to the total volume. This means that every drop of water that exists on Earth today is all the water that will ever exist on Earth. There will never be more. We cannot manufacture water on a meaningful scale. We can only manage, conserve, and protect what we have. This fact gives extraordinary weight to every decision we make about how we use, pollute, and distribute water. We are stewards of a finite, irreplaceable resource. Let us talk about rainwater and whether it is safe to drink. Rainwater, as it forms in clouds, is essentially distilled water, pure H2O condensed around tiny particles of dust, pollen, or other aerosols. However, as rain falls through the atmosphere, it can absorb gases and pollutants from the air, including carbon dioxide, which makes it slightly acidic, as well as sulfur dioxide, nitrogen oxides, and particulate matter from industrial emissions, vehicle exhaust, and other sources. By the time rain reaches the ground, it is no longer pure. In heavily polluted areas, rainwater can contain significant concentrations of harmful substances. In cleaner environments, rainwater is relatively pure and has been collected and used as drinking water throughout human history. Many communities around the world still rely on rainwater harvesting, collecting rainwater from rooftops and other surfaces and storing it in tanks or cisterns as a primary or supplementary source of drinking water. When properly collected from clean surfaces and stored in covered, well-maintained containers, harvested rainwater can be a safe and sustainable source of drinking water, though most health authorities recommend filtering and disinfecting it before consumption to remove any contaminants it may have picked up from the collection surface or during storage. Here is a fact that reveals the profound disparity in how water is valued and used around the world. While some people struggle to access even a few liters of clean water per day for basic survival, others use hundreds of liters per day without thinking twice. The average person in a water-rich, developed nation uses between 300 and 400 liters of water per day when you include both direct use, drinking, cooking, bathing, cleaning, and indirect use, the water embedded in the food they eat, the products they buy, and the energy they consume. In contrast, the minimum amount of water the United Nations considers necessary for basic human survival, for drinking, sanitation, and hygiene, is just 50 liters per day. And millions of people around the world do not even have access to that minimum. This disparity is one of the great injustices of the modern world, and it is growing as water resources come under increasing pressure from population growth, urbanization, pollution, and climate change. Now let us talk about wells, one of the oldest technologies for accessing drinking water. Humans have been digging wells to access groundwater for at least 8,000 years. The oldest known wells were discovered in Cyprus and Israel, dating back to the Neolithic period. For thousands of years, wells were dug by hand, a dangerous and labor-intensive process that limited their depth to however far human effort could reach. Modern wells are drilled using mechanical equipment and can reach depths of hundreds or even thousands of feet, accessing deep aquifers that hand-dug wells could never reach. Approximately 1 billion people worldwide still rely on wells as their primary source of drinking water. Private wells, which are common in rural areas, are typically not subject to the same regulations and testing requirements as public water systems. This means that the water quality of private wells is often unknown unless the well owner takes the initiative to have it tested. Common contaminants in well water include bacteria, nitrates from agricultural fertilizer runoff, arsenic from natural geological sources, and various industrial chemicals. Health authorities generally recommend that private well owners test their water at least annually for bacteria and nitrates, and periodically for other contaminants based on local conditions. Here is something that reveals the incredible precision of water regulation in your body. You would think that with all the water you drink and all the water you lose, maintaining the right balance would be a chaotic process, but your body maintains its water balance with extraordinary accuracy. An average adult's body contains approximately 40 liters of water, and the body's regulatory systems aim to keep this volume within about plus or minus a few hundred milliliters at any given time. That is a variation of less than 1%. To achieve this, your body integrates input from osmoreceptors in the hypothalamus that detect blood concentration, baroreceptors in the blood vessels that detect blood volume and pressure, and hormonal signals from the kidneys, the adrenal glands, and the heart. These systems work together in real time, adjusting thirst, urine production, and water reabsorption to maintain homeostasis. The complexity of this regulatory network rivals the most sophisticated engineering systems ever designed, yet it operates silently and automatically, every second of every day, from the moment you are born until the moment you die. Let us now explore a fact about water that enters the territory of psychology and perception. Research has shown that simply seeing water, a river, a lake, the ocean, even a fountain or a photograph of water, can have measurable calming effects on the human brain. This phenomenon, sometimes called the blue mind effect, has been studied by marine biologist Wallace Nichols and others. Brain imaging studies have shown that viewing scenes of water activates regions of the brain associated with positive emotions, empathy, and a sense of calm. Hearing the sound of flowing water has similar effects. It reduces levels of the stress hormone cortisol and can lower heart rate and blood pressure. This is why water features are commonly used in spaces designed for relaxation, spas, meditation rooms, hotel lobbies, and gardens. It may also help explain why waterfront property is consistently more valuable than comparable inland property, and why people are drawn to beaches, lakes, and rivers for recreation and relaxation. Our attraction to water runs deeper than practical need. It is wired into our neurology. Here is something that connects water to the world of forensic science. The isotopic composition of water, specifically, the ratios of different isotopes of hydrogen and oxygen in a water sample, varies depending on geographic location. Water from different regions has a distinct isotopic fingerprint based on factors like latitude, altitude, distance from the ocean, and climate. Scientists can analyze the isotopic composition of water found in a person's body, in their hair, teeth, or tissues, to determine where that person has been living or traveling. This technique has been used in criminal investigations to help identify unknown victims, trace the movements of suspects, and even identify the geographic origin of illegally traded products. The water you drink literally becomes part of you, and it carries with it a chemical signature of where it came from. Your body is, in effect, a recording device for the water you consume. Let us discuss a fact that highlights the intersection of water and energy in your daily life in a way you probably never considered. Heating water is one of the largest energy expenditures in most households. Water heating accounts for a substantial portion of total household energy use, typically the second or third largest energy expense after heating and cooling the home. Every hot shower, every load of laundry done with warm water, every dishwasher cycle, every cup of tea boiled on the stove, all of these require energy to heat water. Reducing hot water use, improving the efficiency of water heaters, and insulating hot water pipes are some of the most cost-effective ways to reduce energy consumption and lower utility bills. But there is a broader point here. Water and energy are intertwined at every level of daily life. Saving water saves energy, and saving energy saves water. Every time you turn off the tap while brushing your teeth or take a slightly shorter shower, you are saving not just water but also the energy that would have been needed to heat and pump that water. Here is a fact that reveals something about water and human culture that is both surprising and delightful. Throughout history, humans have attributed healing powers to specific water sources. Hot springs, mineral springs, and holy wells have been sites of pilgrimage and healing for thousands of years. The ancient Romans built elaborate bathhouses around natural hot springs, believing the mineral-rich waters could cure a wide range of ailments. In Japan, the tradition of onsen, bathing in natural hot springs, has been practiced for centuries and remains an integral part of Japanese culture. In Europe, spa towns like Bath in England, Baden-Baden in Germany, and Karlovy Vary in the Czech Republic grew up around mineral springs and attracted visitors seeking health benefits from the waters. Modern science has confirmed some of the health benefits attributed to mineral springs. Bathing in mineral-rich hot water can improve circulation, reduce muscle and joint pain, relieve stress, and improve certain skin conditions. The dissolved minerals, including sulfur, calcium, magnesium, and silica, can be absorbed through the skin and may have therapeutic effects. While not all the historical health claims about healing waters have been validated by science, the tradition of seeking health through water reflects a deep and enduring human intuition about the connection between water and well-being. Let us now address a practical concern that affects millions of people: what to do about water in emergency situations. Natural disasters, infrastructure failures, contamination events, and other emergencies can disrupt or compromise drinking water supplies with little or no warning. Emergency preparedness experts recommend that every household maintain a supply of at least 1 gallon of water per person per day for a minimum of 3 days, and preferably for 2 weeks. This water should be stored in clean, food-grade containers in a cool, dark place and rotated every 6 months to ensure freshness. In an emergency where tap water is not available or may be contaminated, knowing how to purify water from alternative sources can be life-saving. As we discussed, boiling is one of the most effective methods. Water purification tablets containing chlorine dioxide or iodine can also render contaminated water safe to drink. Portable water filters designed for backcountry use can remove bacteria and parasites, though not all filters remove viruses. Even constructing a basic solar still, using a sheet of clear plastic over a container in the sun to evaporate and condense water, can produce small amounts of safe drinking water in a survival situation. Preparation is key, because when a water emergency strikes, it is too late to start planning. Here is one more fact about water and the body that brings us full circle to the theme of this entire documentary: the centrality of water to everything you are. Water is the medium in which every chemical reaction in your body takes place. It is the solvent in which nutrients dissolve and are transported. It is the lubricant that allows your joints to move, your eyes to blink, and your food to travel through your digestive tract. It is the coolant that prevents your body from overheating. It is the carrier that removes waste from every cell. It is the structural component that gives your cells their shape. It is the medium in which your neurons fire, your muscles contract, and your heart beats. Take away water, and every one of these processes stops. You are not a being who happens to need water. You are a being made of water, sustained by water, shaped by water, and ultimately dependent on water for every single function that keeps you alive. The most important relationship in your life is not with another person, it is with water. And as we bring this documentary to a close, let us consider the larger picture one final time. Water is the only substance on Earth that is essential for all known forms of life. It is the only common substance that exists naturally in all three phases on our planet's surface. It has shaped the geology of the Earth, the evolution of life, the rise and fall of civilizations, and the daily rhythm of every human being alive today. It is the most studied substance in science, and yet it still holds mysteries that researchers are working to unravel. It is the most used resource in human civilization, and yet it is increasingly threatened by pollution, overuse, and climate change. It is free in some places and fought over in others. It is taken for granted by many and desperately sought by millions. The water in your glass is not just a beverage. It is a miracle of physics, a product of stellar evolution, a vehicle of ancient history, and the single most important substance your body will ever encounter. It has been on a journey of billions of years to reach you, passing through clouds and oceans, through the bodies of countless organisms, through rock and soil and ice and air. It has witnessed the rise and extinction of species, the birth and death of civilizations, the slow reshaping of continents. And now, for a brief moment, it is part of you, flowing through your blood, cushioning your brain, lubricating your joints, powering your cells. And then it will move on, returning to the cycle, continuing its endless journey through the water system of this extraordinary planet. The next time you pick up a glass of water, pause for just a moment. Consider what you are holding. Consider where it has been. Consider what it does for you. And consider the billions of people around the world who do not have the luxury of taking a clean glass of water for granted. Water is life. It always has been. It always will be. And now you know just a little bit more about why. Take care of your water, take care of yourself, and take care of each other. Thank you for watching this documentary in its entirety. If you found this information valuable, surprising, or thought-provoking, please share it with someone who needs to hear it. Subscribe to this channel for more content that changes the way you see the world. And remember, drink your water.